Hello, and welcome to the 20th lecture in the Jabrah Reinforcement Learning series. So today we're going to start talking about off-policy learning with approximation. So in the previous lecture, we looked at approximate solution methods for estimating the value functions for large state spaces. But if you remember, we were looking at how we do this for on-policy algorithms. So the particular example we're going through was with salsa. Now, in this lecture, we're going to follow the same pattern and try to see if we can actually use the same methods for off-policy learning. And we'll realize that there are certain challenges that come with attempting such a feat. So, let's get started. So we already identified the differences between on-policy and off-policy methods from before. And we saw that off-policy methods actually have greater variance, even though they're more general. And that now when we extend these policies to function approximation, they are actually much harder to deal with. And in this lecture, we'll look at some of these issues and how we can either resolve them or improve on them. So for the off-policy control problem, we said that we have two aspects to it. We are given what we call a target policy and a behavior policy. So a target policy which we denote by pi, a behavior policy which we denote by b, right? And both of these policies would change during learning when we're resolving them for the control problem. And we actually already looked at this before, so I'm not actually going to go through like the definitions of what they are in detail. I mean, in general, like we know that the behavior policy is the one that generates, our behavior, like our episodes and such. And the target policy is what we're trying to learn based on whatever our objective is. So we said that when we're given a target policy and a behavior policy, and we want to estimate the value function of the target policy based on episodes generated by the behavior policy, we use what we call the importance sampling ratio, which denoted as rho t is equal to pi of at, comma, this is given st divided by b. And we said this was our importance sampling ratio. Right. So given this now, and we are trying to sort of extend like our learning to like off-policy, our approximate solution methods to off-policy in this case. Let me actually write down the formula for that. So we had said, let's go back to traditional black. We had said to find the value of Wt plus 1. This is all from the previous lecture, by the way. So I'm just rewriting the formula. We say we have Wt plus alpha times, I'm just going to leave some space here. So we've got Rt plus 1 plus gamma V of St plus 1, comma Wt minus V of St, comma Wt multiplied by the gradient So this basically was our approximate solution methods when we're dealing with, on-policy learning. In this particular case, salsa, or, this is the 2D zero error, as you can see. So we will refer to this as delta t, right? And then we're going to add a new term here. Now this is for, let's say, on policy learning, right? Where our target policy is also our behavior policy. But now, if we want to estimate the value function, like vpi, for the target policy, but we're given episodes from the behavior policy, we said we need to multiply this term by our importance sampling ratio, which we defined here. So I'm going to add this term here, right? And this is our importance sampling ratio. And this is essentially what makes this particular update in this case of policy, right? Because we are adjusting our value functions, of course, based on whatever our behavior policy generated the episode. So this is essentially now our update rule when we're trying to do off-policy learning. Now this alone brings about a set of challenges, especially when we're looking at how great the variance could potentially be when we're doing off-policy learning. So we're going to look at a case of off-policy divergence. So we'll look at the case of off-policy divergence, where we say that, when we try to use this function approximation solution methods for off-policy, the challenge is much greater than what we had when we're dealing with on-policy methods. So it's not so easy to make that direct translation from SARSA as we learned it in our initial lectures, and then we went all the way to semi-gradient SARSA. So when we move from something like, let's say, Q-learning to some version of semi-gradient Q-learning and so forth, there are more challenges that we need to deal with. So in this particular case, we're going to give you this example. So assume we have a large MDP, right? So you start at some state here, S, right? And as usual, you take an action. You end up in some future state, right? That action could have ended you up in a different state or another state, and so on. You remember our backup diagrams, and this is how we've always been doing this. So this is let's say we have a large MDP here, MDP tree or whatever you want to call it. We have a large MDP here, and what we want to do essentially is, let's say we have a transition here, right, from this state to this state. So there's only one action available from this state to this state. So let's say this transition, the value of this state, as you can see, when we're actually dealing with this approximate solution methods, we're trying to learn W in this case, because once we learn W, then we can reliably estimate the value of this particular state, right? So let's say during our learning, we're at a point where W here, usually it's a weight vector, but let's assume this vector only has a single component. And then for whatever reason, the value of this state is actually equivalent to W. And this value of this state is equal to 2W, right? So let's say we're in this position and we're trying to update W using this transition from W to 2W, right? As part of this larger MDP. So let's assume the following. Let's say in the first iteration, we've got W is equal to 10, right? And we have gamma is, approximately equal to 1, so it's close enough to 1. And let's say alpha is equals to 0.1, right? So how would we update this? Well, we would essentially say Wt plus 1, right, is equal to Wt here, which is 10, plus alpha, which is 0.1. And let's assume here, okay, let me write the assumptions, that there's only one action and reward is equal to 0, right? So again, we're looking at this transition here. Okay, we have this transition, our reward is 0, there's only one action, and W is taking these values. So as we were saying, with 10 plus 0.1 times. So because there's only one action, the importance sampling ratio is 1, right? In this case, because we're only dealing with, because only one action is available anyway. So we have this, and then the reward is 0 plus gamma, which is essentially equal to 1, times v of st plus 1, comma wt, so of the future state, which is 2 times w, 2 times 10, which is 20, minus v of st, the value of the previous state, because the transition again is from this state to this state, from this state here to this state here, right? So that's 20 minus 10 times the gradient of this, which is just equal to 1 in this case, right? So here our new value of w is essentially going to be equal to 11, right? So w started as 10, right? And we did this one update, and now it's equal to 11. So what we will notice here is that the values of wt plus 1, right, t plus whatever, they're gonna follow this certain routine. First of all, they're equal to 10, and if you do this update like we did here, then the next iteration they'll be equal to 11. Then the next iteration they'll be equal to 12.1, and this will go on until infinity, right? So we have a case of off-policy divergence whereby we are updating. This is just a simple example, of course, of a larger problem that we will have to deal with. So we've got this case whereby w starts at a certain value, and then as we continuously update it, as we continuously update the transition, it continuously diverges until it reaches infinity, right? Now, if we were to look at this in a more generalized manner, we say that in general, we can rewrite actually our w, like we can say wt plus 1 is equals to wt plus alpha times rho of t delta t. If you remember from above, delta t here is just this entire term. Well, we can call it our TDR in this case, but you understand what it is, times the gradient of v of st, comma wt. And if we substitute, like, let's say we have wt, alpha rho is 1, and then like we're trying to find the value of this constant. So we would have, in this case, 1 plus alpha times 2 gamma, right? Like we're just substituting the values of 2w and w in this equation, right? Minus 1 times wt, right? So what we have here is this constant multiplied by the value of wt. And why is this a problem? because this is actually showing us that in this particular example, right, if we are to substitute, like I didn't actually do the substitution, but you can do it yourself here, where where you can substitute the value of 2w and you can substitute the value of w here, and then see what it actually boils down to. It will boil down to this expression. And what we have is that we are multiplying this constant by wt. And insofar as this constant is greater than 1, then wt will actually diverge all the way to infinity. And this happens whenever our gamma here, our discounting term, is greater than 0.5. And here alpha will be just determining how fast we go to infinity. So it doesn't even matter what the value is, since normally it's between 0 and 1 anyway. And we have this case of off-policy divergence, right? So you might think to yourself that why is this only a problem in off-policy learning? You could imagine how this, how these transitions could happen during on-policy learning, and you would not be wrong in actually imagining that. So we're going to actually look at why this is particularly a problem for off-policy learning, right? So we're going to say in on-policy learning. So let's say we have on-policy learning here, which is our ideal case. And we have our dreaded off-policy learning, at least in this particular scenario. So what we have here is a situation whereby, well, if we look at this transition again, we started off at w, right? So let's, you can actually extend this logic to the continuous case, but to make it easy for you to visualize, just think of this as just think of the episodic case, I guess, in this particular instance. So we go from w to w, right? So what happened to the value of w? So here we increase, right? We increase w in this particular case, as we saw when we're making this transition. Now, what's going to happen, depending on the value of the next state here, so the value of the next state here is either going to be less than 2w, or it's going to be greater than 2w, right? These are the only possible cases here. And if it's actually greater, then it's going to increase this value again. If it's less, in this particular case, this would reduce w. So what happened here? So in on-policy learning, if there is a transition from w to 2w, right, from this state to this state, there also has to be a transition out of this state, right? Because if you think of an algorithm like SARSA or whatever, you go like, well, I'm in this state, I take some action, and I end up in this state. And after taking this action, I increase the value of w. Now that I'm in this state, I'll take another action and end up in a state, let's say this state, where the value of w is less, and then we reduce the value of w. So in this case, like, there is no divergence, right? Because here the value of w increased, here then in the next state it's reduced. So there's, in this simple case, we don't have this divergence problem. But then it could also happen, of course, that we are in this state, we take some action, we end up in this state, we take another action, and we end up in a state that is even greater than 2w, also increasing the value of w, which is a weight vector. But as this is happening, you know that eventually you're going to need to reach some terminal state, right? You're going to need to reach some terminal state. And if the value of this terminal state is actually less than whatever the previous state was, what's going to happen is that we're going to actually reduce the value of W. And if that's not the case, then you can imagine that actually we're representing this appropriately, because like each state is actually trying to lead us towards like the value of each state is actually mostly determined by the cumulative rewards that we get like until the final state. So the guarantee in on-policy learning here is only because we have to have this transition out of 2W. However, in off-policy learning, that does not actually have to be the case. So if we have our W here, and we have our 2W, right, and we have our case here whereby, okay, we're increasing the value of W, right, then you might think, okay, in off-policy, from this state, let's say, I could end up in other states, right? I could take an action that could lead me to another state with a lower value of W or a greater value of W, whatever. But in off-policy learning, that does not actually necessarily have to happen, right? So the reason for that is if the action that is taken by the target policy, right, is not actually taken by the behavior policy, then we're not going to actually update that state, right? Because if you remember, in off-policy learning, we had the assumption of coverage, right? Where we said that when we are trying to find the value of a particular state or a particular, like, we were trying to find the value of a particular state after taking a particular action, so the probability of action given that I'm in a particular state, we also need to ensure that this action is also taken under the behavior policy. So if there are any actions, let me use this, actions not taken, then there is no update. So what that means is that if the actions here, let's say taken by the target policy, not taken by the behavior policy, in this case, then what's going to happen, what's going to happen in this case is that there is not going to be an update out of 2W, right? Or in particular, when we're thinking about if there are actions that are in the behavior policy that are not taken also under the target policy, then again, like for those particular actions, there might be no update. So the guarantees in on-policy learning come from knowing that after I am in this state, I will take another action and there will be an update. But here, depending on whether the action was actually taken under the behavior policy or whether the action was taken under the target policy, there's a potential that there's not going to be an update out of 2W, which means that this divergence might happen. So this is the difference between like why this is a problem for off-policy learning, but not a problem for on-policy learning. Okay, so let's move on. So here the general idea, because particularly in this case, I just showed a simple example of why this might happen, of why this off-policy divergence might happen due to actions that are not taken, depending on the distributions of the target and the behavior policy, and certain actions not being updated might cause us to have this divergence happening. But this is a very particular example, but of course there are more complete examples that we can look at, which I'm not going to do, of course, in this particular lecture because they're just illustrating the same concept. But the idea here is that our updates can be unstable if they are not done according to our own policy distribution, right? So if we're not doing updates according to our own policy distribution, when we're trying to actually, if we're not doing updates according to our own policy distribution, then our updates can actually turn out to be unstable, which is what happens in the case of off-policy learning. So now there are like these dangers of this instability that we're looking at. So our dangers of instability, well, they come in different forms. So first, we have function approximation, where we said that we're generalizing from a large state space, right? Like we are trying to estimate our value function of a large state space. And because of this, we can see why this is necessary. But in the case of like off-policy learning, we also see why this could cause us certain troubles when we're doing our updates that are not in line with our own policy distribution. And another danger of instability is bootstrapping, where we said that we update estimates based on other estimates. And in this particular example, this is an example of bootstrapping, right? When we're doing our TD0 here. So that's another danger of instability. But of course, we need to do that, as we looked at before, if we want to actually learn faster, right? Assuming that we have the appropriate state representation. And then there is also the notion of off-policy training. Right. Where we say that we are training on distributions that are different from those that are produced by the target policy, right? So we still like, of course, we still need to do this. We still need to do off-policy training for reasons that I'm going to go through. Maybe not in this lecture, but in future lectures you'll see why. Because what happens here is that when we have these elements, like we started with simple table learning, whereby we have a very small state space and we actually have a very, we have the model of our environment and so on. But as you can see, the more and more we go to like real world scenarios, we start introducing these things that might make our algorithms unstable, and in most occasions they do. And that's function approximation, but we need to do that. That's bootstrapping, we also need to do that, and there's also off-policy training. Because you might be wondering to yourself, like, why not just do on-policy training if off-policy is causing all these problems? We could just use salsa instead of Q-learning. And of course, we'll soon learn why these methods are important, and that this is particularly in the case of whereby we're trying to learn, let's say, multiple policies, or we're trying to learn from past data and so on. And I mean, the idea of separating the behavior, right, the way we generate our episodes and the way that we learn, is actually quite powerful, and it allows us to learn from examples that we otherwise would not have if we're just sticking to on-policy learning, right? So this essentially is, this was a, relatively short and more theoretical lecture, but the whole idea behind this is just to let us know that off-policy algorithms, they allow us to flexibly deal with the whole notion of exploration versus exploitation. They free the behavior from learning by separating the behavior policy and target policy, as you saw, and they allow us to do parallel learning and so on. And these are some of the reasons why we would want to keep this. It's just that we should know, when we see that our reinforcement learning algorithms are not working, especially when we start going into this like deeper topics. We can actually look at those dangers of instability and see like where the problems could be stemming from, and this could actually help us debug our algorithms, and that is essentially the importance of this lecture here. So with that, I am just going to close it off here, and I'll see you in the next lecture. Thank you.